The night sky is lying to you. Right now, above your head, there are 2 trillion galaxies. 2 trillion. And you can see almost none of them. Not because they're too far away, not because space is empty, but because something far stranger is happening. Something that took us 200 years to figure out. And when scientists finally cracked it open, what they found didn't just change astronomy. It changed what we thought was even possible to know. Stay with me. Because by the end of this, the way you look at the night sky will never be the same. Here is the thing nobody tells you. The darkness above you isn't emptiness. It's evidence. Evidence of the biggest cosmic magic trick ever pulled. And right now, the most powerful telescope ever built is starting to pull back the curtain. What it's finding is making scientists genuinely nervous. Let's go. You're standing outside on a clear night. No city lights, no clouds. You tilt your head back and you see it. Thousands of tiny white dots scattered across black. Beautiful, peaceful, and completely, utterly wrong. Because here is a question that sounds stupid until you actually think about it. Why is the sky dark? Seriously. Think about it for 3 seconds. If the universe is infinite and it's packed full of stars in every direction, then no matter where you point your eyes, your line of sight should eventually hit a star. Every single direction, every single angle. The entire sky should be one continuous blinding wall of light, as bright as the surface of the sun, everywhere. But it's not. And for over 200 years, that simple fact drove astronomers absolutely crazy. This is called Olbers' paradox, named after Heinrich Olbers, who formalized the problem in 1823. But here's what most people get wrong about it. It wasn't just a philosophical curiosity, it was a genuine crisis. Because the math was airtight, the logic was perfect. If the universe is infinite and eternal and full of stars, the sky cannot be dark. It is physically impossible. And yet, there it is, dark. Something is wrong with the universe, or something is wrong with us. Turns out it's both. Before we solve it, let me ask you something. Drop it in the comments right now. When you look up at the night sky, does it feel empty to you? Or does it feel full? I'm genuinely curious, because your answer says something interesting about how your brain processes scale. Let me know below. For a century after Olbers, the smartest minds in science threw everything at this problem. The first suspect was cosmic dust. Makes sense, right? Maybe giant clouds of dust were just blocking the light, like fog on a highway. Simple, clean, wrong. Here's why. Anything that absorbs light absorbs energy, and energy has to go somewhere. That dust would heat up, it would glow, it would re-emit everything it absorbed as infrared radiation. The sky would still be blazing, just in a wavelength your eyes can't see. The dust doesn't solve the paradox, it just moves it. So the dust theory dies, and scientists are left staring at the same dark sky with no answer. The crime scene is clean, and the universe isn't talking. The real answer required something nobody in Olbers' time was even close to imagining. It required us to completely rebuild our understanding of what the universe is, how old it is, how big it is, and how it works. 3 separate revolutions in physics, all converging on one answer. And that answer is so strange that even today most people have never heard the full version of it. Revolution 1. The universe had a beginning. For most of human history, we assumed the universe was eternal, always existed, always will, no start, no end, just infinite time stretching in both directions. And if that's true, then Olbers is absolutely right. An eternal universe full of stars should produce an infinitely bright sky. No question. Then came the Big Bang. 13.8 billion years ago, everything that exists exploded into existence from a single point of unimaginable density. Space itself began. Time itself began. And light began travelling outward in all directions at the only speed it knows, 300,000 kilometers per second. Fast, but not infinite. Here is why that matters. If the universe is only 13.8 billion years old, then light can only have travelled 13.8 billion light years in that time. That's it. That's the boundary. Anything beyond that distance has light that simply hasn't arrived yet. It's still travelling. It won't get here for another billion years, or 10 billion, or 100 billion. We have a horizon, a cosmic bubble. And outside that bubble, for all practical purposes, the universe doesn't exist yet. Not to us anyway. So Olber's infinite forest of stars collapses immediately. It's not infinite from where we're standing. It has a hard edge, a wall made of time. This was huge. This alone should have solved the paradox, but it didn't. Not completely. Because even within that horizon, even within 13.8 billion light years, there are enough stars and galaxies to light the sky many times over. Something else is going on. Revolution 2. Space is stretching. In 1929, Edwin Hubble made one of the most mind-bending discoveries in the history of science. He was studying distant galaxies and he noticed something. They were all moving away from us. Every single one. And the farther away they were, the faster they were moving. This wasn't because the galaxies themselves were flying through space. This was because space itself was expanding. The fabric of the universe, the actual substrate of reality, was stretching, like dots drawn on a balloon being inflated. The dots aren't moving across the balloon. The balloon is getting bigger, and every dot gets farther from every other dot automatically. Now here is where this gets beautiful and weird at the same time. Light is a wave, and when the source of a wave moves away from you, the wave gets stretched. You've heard this with sound. An ambulance siren drops in pitch as it passes you. The sound waves are stretching out. Longer wavelength, lower frequency, lower pitch. This is called the Doppler effect. Light does the exact same thing, but with light, when the wavelength stretches, the colour changes. Visible light shifted to longer wavelengths becomes red, then infrared, then microwave, then radio waves. And here's the punchline. The galaxies that are far enough away aren't just moving fast. They're moving so fast that their visible light has been stretched completely out of the visible spectrum. What was once a bright galaxy blazing with starlight is now sending us radio waves and microwaves. Energy our eyes were never built to detect. The sky isn't dark because it's empty. The sky is dark because it's glowing in colours we cannot see. Right now, above your head, there is light coming from billions of galaxies, hitting your skin, passing through your body, bouncing off every surface around you. You're being bathed in the glow of 2 trillion galaxies every second of your life. And you feel nothing. You see nothing. Because your eyes only work in a tiny sliver of the electromagnetic spectrum, and almost all of that cosmic light is arriving in wavelengths that sliver doesn't cover. That is one of the most staggering facts in all of science, and most people have never heard it. Now pause here, because you might be thinking, okay, so we solved it. Universe is young, light from distant galaxies is redshifted into invisibility. Case closed, Dark Sky explained. But hold on, because the real twist, the one that came in 2016, the one that broke everything we thought we knew about the scale of the cosmos, that twist hasn't landed yet. And when it does, it will reframe everything you just heard. For decades, our best guess at the size of the universe's galaxy population came from the Hubble Space Telescope, and it was genuinely impressive. Astronomers took the deepest, darkest patch of sky they could find, a region so empty to the naked eye it looked like absolute nothing, and they pointed Hubble at it for 10 days straight. What came back was the Hubble Deep Field, and it changed everything. In that tiny patch of sky, the size of a grain of sand held at arm's length, Hubble found over 3,000 galaxies, each one containing billions of stars, just in that single grain of sand of sky. They did the math across the whole observable universe and came up with their number. 100 to 200 billion galaxies. It was a wild number, an almost incomprehensible number. And for 30 years we accepted it as roughly correct. It was wrong by a factor of 10. In 2016, a team of astronomers led by Christopher Consolis at the University of Nottingham decided to do a proper census. And they didn't just look deeper, they looked smarter. They took 20 years of Hubble data and converted the flat two-dimensional images into three-dimensional maps of the universe across time. They were essentially building a time machine out of light. Here is what they found. The early universe was packed. When the universe was young, 1 or 2 billion years old, there were 10 times more galaxies crammed into the same amount of space that exists today. Tiny, faint, ancient galaxies. Hundreds of millions of them. Cosmic building blocks. Most of them too small and too dim for Hubble to see individually. But they were there. Billions of them. Slowly colliding and merging over cosmic time. Building the bigger galaxies we see now, including our own Milky Way, which is itself the product of dozens of ancient galaxy collisions. When Consolis's team accounted for all of these tiny ancient galaxies that have since merged, or that are now too faint and too redshifted for Hubble to detect, they revised the total. Not 200 billion, 2 trillion, 2,000 billion galaxies in the observable universe, and some more recent estimates push it even higher. The James Webb Space Telescope, which we'll get to in a moment, keeps finding more. The number may not have a ceiling we can currently see. Let that sit for a second. 2 trillion galaxies, each one containing on average hundreds of billions of stars, and 90% of them completely invisible to us. Not because they don't exist, not because they're too far away to matter, but because the universe is so old and so large and so active that most of its galaxies have been swallowed up, merged, redshifted into silence, or pushed beyond the edge of what any instrument we have can detect. We have been looking at 10% of the picture, the whole time. Every map of the universe ever drawn, every estimate of cosmic scale ever made, every photograph ever taken of deep space, 10%. And somehow, impossibly, that makes the darkness above you feel even heavier. Because that darkness isn't nothing, it's the other 90%, hiding in plain sight. If you're finding this as mind-bending as I am, do me a favour and hit the like button right now. It genuinely helps this kind of deep science content reach more people who want to actually understand this stuff rather than just hear a surface-level summary. And if you want more videos like this, subscribe. We go this deep every single time. Now let's talk about something the shorter videos on this topic never get to. The thing that is actually keeping cosmologists awake at night in 2026. The James Webb Space Telescope launched in December 2021, and within its first year of operation it started sending back data that made scientists do something rare. It made them publicly say, out loud, that they might have gotten something fundamentally wrong. Here's what happened. The standard model of cosmology, the lambda CDM model, makes predictions about how galaxies form. In the early universe, right after the Big Bang, things should have been relatively simple. Small clumps of matter slowly gravitationally attracting more matter. Building small galaxies first. Then, over billions of years, those small galaxies merge into bigger ones. It's a bottom-up process. Small to large, slow and gradual. JWST looked at the universe when it was only 300 million years old. 300 million years after the Big Bang. The universe was a newborn by cosmic standards, and it found massive galaxies, not little primitive proto-galaxies, massive, fully formed, structurally complex galaxies, some of them comparable in mass to our own Milky Way, existing when the universe was less than 2% of its current age. Under our standard model, this is essentially impossible. There wasn't enough time. The matter couldn't have clumped together that fast. The physics doesn't work. Astronomer Alison Kirkpatrick of the University of Kansas called them the universe breakers. She said, and I want to be precise here, that when she saw the first results she had a moment of genuine panic. Not excitement. Panic. Because if these galaxies are real and as massive as they appear, then something in our foundational model of how the universe works is wrong. Now. There are a few possible explanations. Some researchers think the early universe was just better at turning gas into stars than we predicted. More efficient. The process was the same, just faster. Others think dark matter played a role we don't fully understand yet. Others think there are errors in how we're measuring the distances and masses of these objects at such extreme redshifts. And a smaller group is starting to ask whether the Big Bang model itself needs serious revision. Here's the honest answer. We don't know yet. The data is still coming in. JWST has been operational for a few years now, and we are genuinely in the middle of this scientific debate. This is not settled. This is live science happening right now. And that is one of the most exciting things I can tell you. Here's a question for the comments. Do you think JWST is going to force a major revision of the Big Bang Theory, or do you think we'll find a way to make the standard model work? Drop your take below. I read every single comment on this channel and I'll reply to as many as I can. Let's go back to Olbers for a moment because I want to close this case properly before we go deeper. The night sky is dark. Here is the complete answer. Not the two-sentence version. The real one. Reason 1. The universe started 13.8 billion years ago. There is a cosmic horizon. Light from beyond that horizon hasn't arrived yet. The forest of stars is real, but it's not infinite from where we're standing. It has an edge made of time. Reason 2. The universe is expanding. Everything beyond a certain distance is moving away from us faster than light can close the gap. Not because anything is travelling through space faster than light, which is impossible, but because space itself is expanding, which has no speed limit. The light from those galaxies is being stretched into wavelengths we can't detect. The sky is full of radiation we can't see. Reason 3. And this is the one that should make your jaw drop. Most of the objects in the universe that are producing light are themselves invisible to us. 2 trillion galaxies. 90% of them too small, too faint, too old, or too redshifted for even the Hubble Space Telescope to detect individually. 3 separate physics revolutions, 1 ancient question, 1 dark sky. And here is the beautiful part. That darkness isn't a bug, it's a feature. The dark sky is the universe showing you its own history. Every dark patch is a timestamp, a geological layer of cosmic time. The sky is dark because the universe had a beginning, because it's been expanding for billions of years, because 2 trillion galaxies played out their entire lives too far from us to be seen. The darkness is the receipt. Now I want to take you somewhere most science communicators don't go. Because here's a question that comes up whenever you explain all of this. If 90% of galaxies are invisible even to Hubble, why can't we just build a bigger telescope? One that can see radio waves? One that spans the entire electromagnetic spectrum? Can't we just see everything? This is a brilliant question. And the answer is complicated. We do have radio telescopes. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, the Event Horizon Telescope, which is actually a planet-sized array of radio dishes networked together. These instruments have revealed enormous amounts of structure in the universe that optical telescopes can't see. But here's the problem. Redshift doesn't just dim the light, it dilutes it. When a galaxy is so far away that its visible light has been stretched into radio waves, the energy per photon has dropped by a factor of thousands. The signal is almost unimaginably faint. We're talking about detecting the equivalent of a single photon that has been travelling for 12 billion years and doing it against a background of radio noise from every other source in the universe. It's not impossible. JWST has already started detecting galaxies in the infrared that Hubble couldn't see. Radio arrays have mapped cosmic structure at scales Hubble never could. But the most ancient and most distant galaxies, the ones that have been redshifted all the way into the radio spectrum, remain genuinely beyond our reach with current technology. There is also a more fundamental limit. The cosmic microwave background radiation, the CMB. This is the leftover glow of the Big Bang itself. radiation that has been travelling since the universe was just 380,000 years old. It's everywhere. It's the oldest light in existence, and it forms a wall. We cannot see through the CMB. It is the final horizon. The universe, in its very first moments, was opaque. A dense, hot plasma of particles that scattered light in every direction. Only after the universe cooled enough for atoms to form did light travel freely for the first time. The CMB is that moment, frozen in radiation and stretched across the entire sky. It means there is a hard limit. No telescope, no matter how powerful, can see the universe before 380,000 years after the Big Bang. The earliest moments are permanently hidden behind the last scattering surface. We live inside a bubble, and the walls of that bubble are made of the beginning of time. Take a breath. Because I want to go somewhere even further out now. What does this mean for us? Not for science, not for cosmology, but for us. For what it means to be a conscious creature sitting on a rock in the middle of all of this. We can see, with our naked eyes, on a clear dark night, somewhere between 2,000 and 5,000 individual stars. That's it. 2,000 to 5,000 out of the approximately 400 billion stars in our galaxy alone. And our galaxy is one of 2 trillion. With a basic telescope, you can start to see some of the closer galaxies. The Andromeda Galaxy, our nearest large neighbour, is visible as a faint smudge on a dark night. You're looking at 1 trillion stars as a smudge. The Hubble Deep Field, that grain of sand patch of sky I mentioned earlier, contains over 3,000 galaxies in a region too small for your eye to even resolve as a point. If you took that patch and tiled it across the entire sky, you'd have enough data to map out hundreds of billions of galaxies from a single telescope in orbit, and that's still only 10%. There is a version of this universe where you could see all of it, where the electromagnetic spectrum was tuned to human eyes, where redshift didn't exist, where the expansion of space slowed the light to match our biology. In that universe, the sky would be one continuous surface of glowing light. No stars, no individual points, just a wall, a ceiling, a floor. Every direction a blinding glow from the accumulated light of 2 trillion galaxies across 13 billion years of cosmic time. That universe would be unrecognizable. Life as we know it might not be possible. The energy alone would sterilize everything. But in that universe, Olbers would be right, and nobody would wonder why the sky is bright. We live in a universe where the darkness is a gift, where the expansion of space is running interference on behalf of life, diluting the cosmic fire down to background radiation cool enough for carbon chemistry to exist, cool enough for you to exist. You are reading this because the universe expanded fast enough and old enough that the sky is dark. Let me tell you about the fate of that sky, because this part doesn't get talked about enough. Right now, we can observe roughly 2 trillion galaxies across a horizon of about 46 billion light-years in every direction. That's our full observable universe, and it's astonishing. But it won't always be that large. The expansion of the universe is not slowing down. It's accelerating. Something called dark energy, which we don't fully understand, is pushing space apart at an increasing rate. The farther away a galaxy is, the faster it's receding, and there is a distance called the Hubble radius, beyond which galaxies are already receding faster than light. Those galaxies are already gone, already unreachable, already functionally outside our universe. As time goes on, more and more galaxies will cross that threshold. Their light will never reach us. They will disappear. Not because they're destroyed, not because they move through space, but because space itself carries them beyond the reach of physics, beyond the reach of communication, beyond the reach of everything. In 100 billion years, the universe will have expanded so much that all of the currently observable galaxies outside our local group, the Milky Way and its handful of neighbours, will have receded beyond the Hubble radius. The night sky in 100 billion years will contain no other galaxies. None. Just our local group, eventually merging into one giant elliptical galaxy floating alone in an expanding void. The astronomers of that era, if any exist, will have no evidence that other galaxies ever existed. No redshift to measure, no cosmic microwave background to detect. It will already be too faint. No data, no clues. They will look at the sky and conclude, logically and incorrectly, that the universe consists of exactly one galaxy. Theirs. Every conclusion they draw about cosmology will be wrong, not because they're stupid, but because the evidence will be gone. We happen to live in a very special moment, a window of cosmic time where enough of the universe is still visible to piece together its history. The universe is 13.8 billion years old. We can see the CMB, we can see the galaxy distribution, we can measure the expansion rate, we can detect the echoes of the Big Bang. In 100 billion years, that window will be closed, permanently. We're living in the only era where the universe can know itself. That should not be a small thing to you. The fact that you exist right now, in this exact moment of cosmic time, when the universe is still readable, still mappable, still comprehensible, is not nothing. It might be everything. If this video is making you see the universe differently, drop a comment and tell me what hit you hardest. I genuinely love reading these. And if you want to support what we're doing here, the super thanks button is right below the video. Every single one of those goes directly into better research, better audio, better content. We appreciate everyone. Let's talk about what JWST is actively doing right now in 2026. Because it's not just finding impossible galaxies, it's doing something even more remarkable. It's beginning to see the hidden 90%. JWST operates primarily in the infrared spectrum, the wavelengths of light just beyond what human eyes can detect. And this turns out to be exactly the right tool for seeing galaxies that have been redshifted out of the visible range. JWST is essentially a translator. It takes light that the universe has been silently broadcasting for billions of years, in a language our eyes don't speak, and converts it into images. The first deep field image from JWST was released in July 2022, and the response from the scientific community was almost uniformly the same: disbelief. The image covered a patch of sky comparable to a grain of sand held at arm's length. It showed thousands of galaxies, in extraordinary detail, galaxies so far away that their light was emitted when the universe was only a few 100 million years old. Galaxies that Hubble could barely detect as faint smudges, resolved into spirals and ellipticals and irregular forms. And between the galaxies, in regions that Hubble saw as empty dark space, JWST found more galaxies, smaller, fainter, earlier. The hidden population is not hypothetical, it's real. We are looking at it, and it's more populated than our models predicted. Over the last 3 years, JWST has catalogued thousands of these previously invisible galaxies, and the pattern is consistent with the Constellus team's prediction. The early universe was densely packed. The galaxy count is real. 2 trillion is probably a floor, not a ceiling. What makes this remarkable is that we built a machine, launched it 1 million miles from Earth, aligned 21 gold-plated beryllium mirrors to nanometer precision in the vacuum of space, cooled its instruments to within 40 degrees of absolute zero, and we're now using it to count galaxies that have been invisible since before Earth existed. That is the most stunning proof of human intelligence I have ever encountered. Not artificial intelligence, not algorithms. The raw ambition of a species that looked up at the dark sky and said we need to know what's in there. All of it. Even the parts we can't see. I want to address something directly, because whenever a video like this gets made, the comments fill up with a very predictable response. People saying the Big Bang is just a theory. People saying we can't know any of this. People saying scientists are making it all up or working from assumptions. And here's what I want to say to those people honestly and without condescension. You're right that it's a theory. All of science is theory. That word doesn't mean guess, it means a framework supported by evidence. and the Big Bang is supported by an extraordinary convergence of independent evidence. The cosmic microwave background, which is precisely what you'd expect from a hot, dense early universe. The abundance of light elements like hydrogen and helium, which matches Big Bang nucleosynthesis calculations almost exactly. The large-scale structure of the universe, how galaxies cluster and filament, which matches simulations of an expanding universe from a single point. The redshift of distant galaxies, the age of the oldest stars, which are consistent with but not older than the age of the universe. None of these lines of evidence were designed to support each other. They come from completely different instruments, completely different teams, completely different physics, and they all converge on the same answer. Could the model be wrong in some details? Almost certainly yes. The JWST data suggests there are things we don't fully understand about early galaxy formation. That's how science works. You find the edge of what your model can predict and you update it. Could the entire Big Bang framework be wrong? It's theoretically possible. But you'd need to explain all of the evidence above with something else, and nothing else currently does that. The model isn't perfect, but it's the best map we have. And maps that are imperfect are still useful. They still get you somewhere real. Now. One more thing before we bring this home. I want to talk about what you can actually do with all of this. Not in a practical sense. There's nothing practical about 2 trillion galaxies, but in a cognitive sense, in the sense of what it means to be the kind of creature that can understand this. You are made of atoms. Atoms forged in the cores of stars that lived and died before our sun was born. The iron in your blood was made in a supernova. The calcium in your bones was made in a star's final collapse. The carbon that makes up everything complex about you was scattered across space by stellar winds billions of years ago and eventually gravitationally collected, along with everything else, into this solar system, this planet, this biosphere, this body. You are, quite literally, the universe looking at itself. And right now, you're the universe understanding that it's mostly hidden from itself. That 90% of what exists cannot be seen with the instruments evolution gave us. That we live in a brief window of cosmic time when the universe is still legible. That the darkness above you is not emptiness but evidence. Not nothing but everything we can't reach. Olbers looked up at the dark sky and saw a paradox. A crime scene. A mystery. We look up at the same dark sky and see 13.8 billion years of history. We see the fingerprint of the Big Bang in the background radiation. We see the recession of 2 trillion galaxies in the redshifted silence. We see the merger history of the early universe in the large-scale structure. We see the story of everything that has ever happened, written in light and darkness across the entire sky. The universe has been hiding, but it left evidence everywhere, and we found it. But I want to go one layer deeper than that, because I think the most underappreciated part of this entire story is not the 2 trillion galaxies. It's not the redshift. It's not even the JWST. It's the fact that a species that has existed for roughly 300,000 years on a planet that has existed for 4.5 billion years, orbiting a star in one of 2 trillion galaxies, figured any of this out at all. Think about the chain of events required. First, we had to survive long enough as a species to develop agriculture. Agriculture gave us surplus food. Surplus food gave us time. Time gave us the leisure to sit and watch the sky and wonder. From that wondering came mathematics. From mathematics came physics. From physics came telescopes. From telescopes came the discovery that those smudges of light weren't clouds. They were entire galaxies, each one a universe unto itself, separated from us by distances so vast that the light we're seeing left before our planet existed. That is the chain. Every link is fragile. Every link required thousands of years and millions of people building on each other's work, most of them never knowing what the chain would eventually produce. And we didn't stop there. We looked at the light from those distant galaxies, and we noticed it was shifted red. We realized that meant they were moving away. We realized that meant space was expanding. We traced that expansion backward mathematically and concluded that everything had to have started from a single point. We then predicted what that would have left behind: a faint uniform glow of microwave radiation permeating all of space. And then we built instruments sensitive enough to detect it, and there it was, exactly where we predicted, exactly the temperature we calculated, 13.8 billion years old. We predicted the echo of creation, and then we heard it. That is not a small thing. That is, by any measure, the most extraordinary intellectual achievement in the history of life on this planet. And we did it without leaving the neighborhood. Almost everything we know about the cosmos we figured out from right here, from this pale blue dot orbiting a middling star in the outer arm of one completely ordinary spiral galaxy among 2 trillion others. We have physically sent spacecraft only as far as the outer edge of our own solar system. Voyager 1, our most distant emissary, has travelled 47 years and is still inside our solar bubble. Still not even close to the nearest star. And yet from here we have mapped the entire observable universe, traced its history back to its first fraction of a second, and counted galaxies that existed before Earth was born. What we don't know yet is just as extraordinary as what we do know. We don't know what dark energy is, the force that is accelerating the expansion of the universe, the thing that will eventually isolate us in a void of our own, pushing every other galaxy beyond the horizon. We've measured it. We've confirmed it. We've named it. And we genuinely have no idea what it is. It makes up roughly 68% of the total energy content of the universe, the dominant force in existence, and it is completely mysterious. We don't know what dark matter is either, the invisible scaffolding that holds galaxies together. Without it, the stars in the Milky Way would fly apart. The galaxy wouldn't exist. You wouldn't exist. Dark matter makes up roughly 27% of the total energy content of the universe. The second dominant force. Also completely mysterious. That means everything we can see, everything we've ever touched, everything made of atoms, every star, every planet, every galaxy, every person who has ever lived, all of it together makes up roughly 5% of what the universe contains. 5%. We are made of the rounding error, the fringe, the footnote at the bottom of the cosmic ledger, and yet from inside that 5% somehow we have mapped the other 95. We have detected it, measured it, theorized about its nature. We haven't solved it, but we know it's there. We know roughly how much of it there is. We know how it behaves gravitationally even though we can't see it. That is either the most humbling fact you've ever heard, or the most inspiring one. Probably both at the same time. There is one more thing I want to say about this. Something that I think gets lost in the pure scale of all these numbers. Science communicators, myself included, spend a lot of time trying to make the scale of the universe feel personal. We use metaphors. We say things like, if the Milky Way was the size of a dinner plate, the observable universe would be the size of North America. Or if the Big Bang was 1 second ago, all of recorded human history would be the last microsecond of that second. These analogies are useful. They help. But they also, in a strange way, push the universe further from you. They make it feel like a statistic, something that happens to be very large, a number you acknowledge and then set down. But here is what I want you to feel instead. Every photon of light that hits your eye when you look at the night sky has been travelling. Really travelling. Physically moving through space, in some cases for millions or billions of years. The light from the Andromeda Galaxy takes 2.5 million years to reach your eye, meaning the photon that hits your retina tonight left Andromeda 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. That photon has been travelling the entire history of humanity, the entire span of everything we have ever built or thought or felt, and it ends its journey in your eye tonight. That is not a metaphor. That is literally what happens when you look up. the light from the most distant galaxies JWST can detect left when the universe was only a few 100 million years old. No stars like our sun existed yet. No rocky planets. No chemistry complex enough for life. Just ancient gas and the very first primitive galaxies clumping together in the dark. That light has been travelling for 13 billion years. It passes through intergalactic space, through the expanding fabric of the cosmos, through the local group, through the outer halo of the Milky Way, through our solar system, through Earth's atmosphere, through the optical systems of one of the most sophisticated machines humanity has ever built. And it ends up as a data point in a FITS file on a hard drive at the Space Telescope Science Institute in Baltimore, Maryland. And from that data point, we reconstruct a galaxy that no longer exists in the form we're seeing. It has aged, grown, merged, changed beyond recognition over the last 13 billion years. What JWST sees is a ghost, a photograph of something that has been dead in its original form for billions of years before Earth was born. Every image from JWST is a photograph of something that no longer exists as it appears. We're doing archaeology across the entire history of the cosmos, and the artifacts are made of light. I think about this a lot, about what it would mean to know all of it, not just the observable universe, but everything. If dark energy is some kind of field, what generates it? What is its source? Is it constant, or does it change over time? If it's constant, then the heat death of the universe is inevitable. Everything cools, everything spreads, the last black holes evaporate in a Google years. After that, nothing. Not darkness, not silence, not emptiness. Just the absence of any structure capable of experiencing anything at all. But if dark energy changes, if it weakens or reverses, then maybe the expansion slows, maybe it reverses, maybe the universe collapses back in on itself in what cosmologists call the Big Crunch. And maybe from that crunch comes another bang, and another universe, a cycle with no beginning and no end. Or maybe the universe tears itself apart first. If dark energy grows stronger, the expansion accelerates beyond a critical point and the fabric of space begins to rip. Not just galaxies receding beyond our horizon, the very atoms in your body being pulled apart by the stretching of space. The big rip. Every particle in the universe separated from every other particle by infinite expanding space in a finite amount of time. These are not science fiction scenarios. These are real outcomes that current physics cannot yet rule out. The fate of everything depends on a number. The equation of state of dark energy, a parameter called W. If W equals -1, you get the steady heat death. If W is greater than -1, maybe things collapse or cycle. If W is less than -1, the big rip. Right now, our best measurements put a W very close to -1. But the error bars are large enough that we can't be certain. We are living in a universe whose ultimate fate we do not yet know. And the instrument that might give us the precision to find out is JWST, along with its successors. The Nancy Grace Roman Space Telescope, planned to launch in the late 2020s, will survey the sky at infrared wavelengths across a field of view 100 times larger than JWST's. It will map dark energy across cosmic time with a precision that current instruments can't approach. It will measure the expansion history of the universe at enough different epochs to determine whether dark energy is truly constant or whether it's been changing. That measurement might tell us which fate awaits everything. We are, within the next decade or two, potentially going to know the answer to the most fundamental question in cosmology. Not just what the universe is made of, but how it ends. That is the world you live in. That is the science happening right now. Not in science fiction, not in speculation, in peer-reviewed journals and telescope operations centres, and graduate student dissertations being written tonight somewhere on Earth, by someone who might be the person who figures it out. And here's what I find most remarkable about all of it. The people doing this work are not superhuman. They're not different from you in any fundamental way. They are people who got curious, who pursued that curiosity, who built on the work of people before them, and who showed up. That's the whole formula. Curiosity plus persistence plus the accumulated knowledge of everyone who came before. Olbers was just a doctor who liked astronomy. He didn't have a physics degree, he didn't have a university position. He was a physician in Bremen who spent his evenings looking at the sky and asking questions. The question he asked echoed for 200 years and required the combined work of Einstein and Hubble and Penzias and Wilson and Consulis and hundreds of others to finally answer. A question asked by a doctor in 1823, answered by a space telescope in the 2020s. That is how this works. Nobody knows which question will unlock the next revolution. Nobody knows which curious person will ask the right thing at the right time. The only way to find out is to keep asking, which is, in the end, what this channel is. Us asking together. Olbers looked up at the dark sky and saw a paradox, a crime scene, a mystery. We look up at the same dark sky and see 13.8 billion years of history. We see the fingerprint of the Big Bang in the background radiation. We see the recession of 2 trillion galaxies in the redshifted silence. We see the merger history of the early universe in the large-scale structure. We see the story of everything that has ever happened, written in light and darkness across the entire sky. The universe has been hiding, but it left evidence everywhere, and we found it. Let me close with this. The fact that we solved Olbers's paradox at all is maybe the most underrated achievement in the history of science. Not because the answer is beautiful, though it is, but because of what it required. It required us to discover that the universe had a beginning, that space is expanding, that light has a speed limit, that there are 2 trillion galaxies, that 90% of them are invisible, that time is a horizon as real as any wall. We had to rebuild our entire understanding of reality to answer a question a child could ask: why is the sky dark? And the answer is, because the universe is enormous and old and expanding and mostly beyond our reach. But not unknowable, never unknowable, just waiting for us to build better eyes. JWST is those eyes, and it's only just getting started. I'll leave you with one question for the comments. If you could point JWST at any object, any region of space, any question in cosmology, what would you want it to look at next? What mystery would you most want answered? Drop it below. Some of the best ideas for future videos on this channel have come directly from your comments. And if this video made you think differently about the sky above you, I'd love to know. Tell me in the comments, hit the like button if it was worth your time, subscribe if you want more, and if you really want to go deep on this stuff, the super thanks is right there. Every single one matters more than you know. The universe may be 90% hidden, but we're going to find it anyway. See you in the next one.